accommodating the change to our start time from here through to the end of the course. Just a couple of housekeeping items. The links to the weather data sources assignment were broken. So I fixed them this morning, so everything should be good to go. And then just a reminder that all the assignments are still going to be due at 11 o'clock Mountain. So you have the entrapment and the safety zones that are due by 11 today if you haven't had a chance to get those in yet. And other than that, I think we are on track. I'm going to turn it over to Richard. You have Richard and weather all day. So, well, I'm kind of excited. I always need to dust off my weather every now and then. If you're not in it every day, it's easy to forget things. All right, so take it away, Richard.
All right, thanks, Tanya. And of course, the weather that we touch in here is just a tiny little smidgen of weather topics out there that cover some important points. So today we'll have 3 separate modules. I'll have a break in between, so I'll probably do one, have a break, do another one, have a lunch break, and then do the third. I see the block goes to 3 o'clock Mountain Time this afternoon, and that's 5 hours, and even with an hour lunch break in there, maybe we can try to finish up a little earlier than the end of the block. I guess there's one more next week to deliver as well. Before we get going here, I just want to try to share my web browser. So just wondering if you're seeing a bunch of file names. Anybody just give me a yes or a no there? And
yeah, we are.
Yep. Okay. So yeah, if you go into your files, there's all of these things here, and there's right at the very bottom of the list, there's the WFBS spreadsheets 2016. We don't actually use those for an assignment, but we do refer to it within the module. So if you want to find it, it is down there, and just above that is a weather folder. So if you go into the weather folder, there's a couple of things called stuvdiagram.pptx, should be the third one down. And 2 down below that, thermodynamic diagram.pdf. They're really exactly the same thing, just 2 versions of this very simple thermodynamic diagram. So yeah, there will be a little bit of work involving them. So whatever is easiest for you, you can make a copy of the PowerPoint and plot points on it, or maybe you can just make a copy of the image and using paint or something, maybe you can paint some dots over it. So we'll be plotting some temperatures, with height. Just a very simple exercise or 2. But that's where those items are located. So just bear with me. I'm going to stop sharing that and bring up the first PowerPoint, which is atmospheric stability. So you should see the title slide now, weather and atmospheric stability. Is that coming through all right?
You bet.
Yeah.
All right. Okay, so here we go. So some of the objectives here, identify atmospheric stability types, and you might see the word stability or instability, and really it's the same thing, just kind of maybe a positive or negative viewpoint on the same type of thing. Or I'll talk about the definition a little bit more as we get into the slides here, so I won't go over it right now. Difference between dry and moist adiabatic lapse rates, and there's a big fancy word for you, adiabatic. If you haven't seen that before, we'll explain that. And it is a little different between dry air and saturated air. We'll understand how atmospheric stability or instability may affect fire and smoke. And this kind of leads into some of the other modules that you'll see during this course as well. A little bit later in the week, and then next week as well, as we talk about some other upper air influences. And we'll introduce some thermodynamic diagrams and perform some simple temperature plots. So we'll see a variety of diagrams, and we don't expect you to memorize all of those. We'll just be using a very basic one in here, but there are some important points to remember on any thermodynamic diagram, and we'll bring that to you as the slides come up here. So when we talk about stability in this sense, we're really talking about convection, the ability of the air to rise or fall. I also use kind of a baroclinic or synoptic instability, which really talks about kind of upper air weather patterns and whether they're going to be, subject to decay into a low pressure area, or maybe building up into a ridge. So it's kind of a completely different concept, which we don't talk about in here. So with the convective stability or instability, it's the atmosphere's resistance to move up and down vertical motion. So we've got three conditions: a stable atmosphere, air parcel doesn't want to rise, neutral, you can lift an air parcel and it's going to stay at its height that you lift it to, or unstable, it's going to try to turn over. So if you can think about having a colder, denser air over top of a kind of a warm, lighter air, it's going to try to turn over, just like if you overload a boat or something like that, it might tend to be a bit more tippy. So, we talk about air parcels here, and really it's kind of like a balloon concept. You can fill a balloon with hot air and it tends to rise. If that air inside there cools off, well, it might sink. With a balloon, there's no transfer between the outer atmosphere and what's inside the balloon. So that's what adiabatic means. No mixing with the environment. So your air parcel is free to rise and fall, but does not mix with the air outside that concept of the air parcel. It can expand or compress, and if you watch my little preliminary audio PowerPoint, we talked about the ideal gas law in there. So, with the increasing temperature, you have to have an increasing pressure, or the volume changes. So you can have your air parcel change in size, but there's still no exchange with the outside environment. So we usually talk about just kind of a unit mass or volume of air, maybe a cubic meter or a kilogram or something like that. So if it expands, your kilogram of air is going to cover a little bit more volume. It's going to take up a bit more space. And if it compresses, you've still got a kilogram, but it's going to be occupying a smaller space. So here's looks like an old diagram from Mars or someplace from 1970. Nice red sky. Well, there are some trees there, so maybe it's not Mars, but anyways, the diagram's old, but the concept remains the same. So at the top here, we've got a stable air mass. We've got wind blowing or lifting air up over a mountain range, and if the air is stable, it's going to try to return to that same level that it started at on the other side. Down below that, neutral stability, if you lift that air parcel up, it's going to try to stay at the same height that you lift it to up there. And on the right-hand side, of course, if you have an unstable air mass, once you lift that air, it's going to try to keep going up. So, that's just kind of a little sidebar here. It's kind of a diagram that you might have heard the term mountain plain circulation before, and this kind of illustrates that concept too, where you've got maybe air flowing in from a flatter prairie region, gets lifted up the side of a mountain, and then you get showers or thunder showers developing close to that mountain range. And a very similar concept, need a little bit of instability, cooler air up above to make that happen. So with the stable atmosphere, we have warm air over top of cool air. There's another term for you in green here, potential temperature. We'll see that on the thermodynamic diagrams. It rises with height, so we'll explain that a little bit more later on. The lifted air parcel, of course, is cooling as it lifts, so it is cooler than the environment, so it tends to try to sink, or it's only going to be able to be lifted so high, and then it stops. Neutral atmosphere, potential temperature is constant. Lifted air parcel doesn't really change temperature. Still the same as the environment, so it's got no tendency to move either up or down. And the unstable atmosphere, we've got cooler air up above warm air. The potential temperature falls with height, and the lifted parcel is warmer than the environment, so it's going to have a tendency to keep rising. Inversions. So with a stable air mass, we have an inversion, usually warm air overlaying cool air. There's different ways that you can get these happening. Katabatic flow, once again, another big fancy word in green there. So that's actually the kind of the downslope flow. And it might occur in valleys, off mountain slopes and things like that. But you can actually, I think having anabatic or katabatic flow just in the upper atmosphere too with frontal systems. And the anabatic is lifting, katabatic is sinking. Advection. So in red here, we've got maybe a lake or ocean out there or something, and we've got a certain layer of air that's blowing in off the ocean. Might be warm air comes out above cooler air at the surface, so that creates an inversion, advection, inversion, and that quite often leads to fog and things like that as well if you're near a big patch of water. Radiation at night. So at night, the land tends to lose its heat a little bit more rapidly than the air. So you've got cooling near the surface, and the air above stays a little bit warmer. So a lapse rate, a change of temperature with a change of altitude or elevation. And we've talked about the adiabatic process, no mixing of environmental air with the air parcel. And we've mentioned the dry or wet, moist adiabatic lapse rate. So we'll get into a bit more details about those here. So the dry adiabatic lapse rate might be abbreviated DALR. We've got that gamma symbol, gamma D equals G, force of gravity divided by the CP, the heat content of dry air there. So degrees Celsius or Kelvin per meter. It's actually a very simple equation. So yeah, not too much fancy there. It works out to about 3 degrees Celsius per 1,000 feet or 9.8 Celsius per kilometer. So roughly about 10 degrees per kilometer. So if you have your air parcel rising 1,000 meters above the surface, well, it might drop about 10 degrees during that ascent. On the other hand, sinking air compresses and warms, and that leads to the potential temperature theta. It might be abbreviated with that symbol theta there. Just, I guess a word of warning here, we use this for potential temperature, but if you're doing geometry and things like that, it might also represent just kind of a generic angle in some type of geometric shape. So just have to be aware of context. Moist adiabatic lapse rate. So we've got saturated air. Air rises to a certain level, and as it cools, it'll eventually reach the dew point. Then we've got saturation occurring. So once we get that saturation occurring, then we start using a different lapse rate, the moist or wet adiabatic lapse rate, or MALR. It's got a lower value at most temperatures than the dry adiabatic lapse rate. So about half of what we have for the dry adiabatic, 1.5 degrees Celsius per 1,000 feet, or 5 Celsius per kilometer. But it does vary with temperature, so it's a much more complex equation to arrive at. With the dry adiabatics lapse rate, we've only got 2 parameters that go into that. With the moist adiabatic, it's a much more complex equation. Once we get to really cold air, though, it tends to equal out to the dry adiabatic lapse rate, so it does curve, and as you get higher up in the atmosphere into colder temperatures, the 2 lines that represent both the moist and the dry adiabatic lapse rate will tend to converge. Now, if you have moist air and it sinks, well, it's going to compress and warm, so as soon as you leave that saturation point, then you have to follow the dry adiabatic lapse rate down to whatever level you want to take that air parcel to. Just in the diagram here, we've got the saturation point, lift condensation level. So if we've got air lifting up here, it gets up to that point, you get saturation, you get condensation, and then you might have cloud formation. When we apply inversions to fire operations, if we have an inversion present, well, we get dense smoke near the ground, and here's a nice, beautiful mountain valley, but it's just completely filled with smoke, and it's not really escaping anywhere. There might be a little bit of outflow through some of the side valleys there, but the bulk of that smoke is just sitting there in place, and it's being trapped by probably warm air sitting up near the mountaintops, not letting anything get out. You might see this term fumigation in green here too, and I think it's usually applied to smoke emanating from smokestacks and other types of chimneys and things like that. But really, the concept is the same. The smoke comes out and just hugs the ground, doesn't disperse very well, and then you've got really heavy concentrations at ground level. Of course, that has impacts on people's health. It might have impacts on fire operations. Maybe aircraft can't fly, for example, because the visibility is too bad. So all sorts of problems can happen with that. And once again, crew safety is affected in various ways. And try to relate a lot of this back to safety. When you're out on a fire, if you can't see very well, you might have some problems. So, visibility is one thing, like human visibility, aircraft for sure. There's other things that we'll talk about, if that inversion happens to break, and, that's a really important concept in fire operations too. So you might have smoke hugging the ground at one point, and maybe the fire activity isn't really that active, but if you do get that inversion breaking, and then suddenly you're into a kind of an unstable situation, it can really affect the fire intensity. We'll talk about that a lot in a lot more detail over the next couple of modules, I think. Well, one more today and then one next week. So inversion breaks, fire intensity increases. You get improving visibility near the surface, but if you're up above that fire when the inversion breaks, well, you've got to be really careful, because you might get sudden, rapid spread of that fire up the mountain slopes, for example. And then, if it's really unstable, well, you might get a plume-driven fire. So we've got a fairly unstable looking atmosphere here with that smoke pretty much going straight up. And, it's in a really unstable atmosphere, you might get a really tall column there. And once they get up to a certain point, then they start to generate their own weather as well. So something to be very cautious of. And that's one reason why the forecast of breaking inversions is quite important in fire operations. So if we look at this plume here, what is it showing? Well, kind of at the bottom here, it's rising quite readily. So definitely unstable air near the surface. We don't see the top here, so we're just going to advance a little bit more. See the plume a little bit more fully here, so pretty good column. It's rising. I don't know how high it is above the mountain peaks there, but maybe at that point we reach an inversion layer. It looks like some of that smoke might be spreading out to the left there. So pretty unstable near the surface, but a bit more stable up top. But still, I think, in this case, we've got pretty good dispersion here, but maybe a fairly active fire. And you can see a bit of flame just on the right-hand side of that. Just zooming into that area. I don't know if that was exactly the same photo or not. Maybe you can just see a hint of that in the middle photo there. But I think this maybe looks a bit brighter, so it might be a little bit, looks like it's a bit later in the series here. So, there are some rough ways of estimating atmospheric stability just from surface observations. And some of those might use, temperature, solar radiation, cloud types, things like that, wind speeds. So I guess that sun angle is fairly important, and we'll talk a bit more about different stabilities at different times of the year here when we talk about venting. We'll cover that later this afternoon, so won't really discuss it too much here. The map that I'm showing here is an example of the Lavdis 1986 dispersion index. So Leonidas Lavdis developed this in the southeastern United States, but then it was expanded by Pascal and Gifford just to estimate stability with ground-based observations. And you can see a kind of a very rough map here, just covering Canada, where we've got blues or greens, which indicate unstable atmosphere. Neutral, kind of in the middle, light green or yellow, and very stable if we get into the orange or red. So early July, we've got kind of a mix here, but I think, for the most part, the country's looking pretty neutral at the time. But there are some areas where you can definitely see some instability showing up here in these kind of light blue areas, a lot kind of scattered throughout the east and a little bit in southern parts of the western provinces. So just with that very bottom point, I'll talk about this a little bit more in the venting talk, so that'll be later today. So let's start to introduce some thermodynamic diagrams. So what do we need? Well, we need some upper air data. So the thermodynamic diagram is a plot of temperature or humidity or wind speed with height. So that might be from highballs, miniature weather balloons or big weather balloons, aircraft, things like helicopters, or kind of I guess other types of aircraft that may measure different temperatures and things with height as well, but you don't usually get a very vertical profile. With the weather balloon or helicopter, you can maybe get as close to vertical as you can, given the wind conditions at the time. So other things as well that could be used in some places, a drop sonde, an instrument dropped out of an aircraft, and instead of measuring things on the way up through the atmosphere, it'll measure things on the way down. Rocket sondes, probably not too useful in the lower part of the atmosphere. I think those are probably more useful for, really, I guess, deep profiles where you get up well into the stratosphere, for example. So we do have a number of upper air stations across North America, and you can kind of see the scattering of that on the map in the lower right-hand corner. So that's the University of Wyoming example. In their case, you can click on the map where there's a station and get the profile. You can either get the text list, or you can actually get an image. You can choose the dates, unit types, and things like that. Or you can just punch in a station number up here. So yeah, I showed some of that yesterday during the weather data sources talk. Now, I guess from the very beginning here, this is these things are going to look really confusing, I think, until you get used to them. The emagram is kind of the old style thermodynamic diagram. In Canada and other parts of probably Europe, that's been replaced by the TFI or tephigram. We'll talk about that shortly. There are important things to remember on all of these, and this is really an important point here, is that each type of thermodynamic diagram has isotherms, lines of equal temperature. In this case, they're vertical, just straight up and down. You got some kind of a pressure or height level, so those are horizontal, or usually very close to horizontal. In this case, they're pretty much horizontal, indicated by the heavy black line here. Mixing ratio, it's kind of a dashed line just slanting slightly upwards to the left, in this case, represented by my brown kind of heavily dotted line. Dry adiabats, solid line extending to the left. We've got it represented in green. If anybody is colorblind, I hope this doesn't cause too much problem, but you can see these appear as I pop them up Then the moist adiabats, which I've got in kind of a light blue dashed line, and they appear in the black dashed line on this particular diagram. So you can see a bit of a curve to that as we leave the surface, kind of curves off to the left. And as we get higher up in the atmosphere, you can see that the upper part here is pretty much parallel to the solid black lines, the dry adiabats up there. So I don't expect you to remember which way these lines run on every diagram. The important thing is that each of these diagrams all have this type of line. If you go to the T phi or temperature phi, the phi is used for entropy or heat content or kind of degree of disorder within the atmosphere. This is commonly used in Canada, probably in the United Kingdom here. If you looked at one from Environment and Climate Change Canada, they might be using the taphogram here. So once again, we've got the isotherms, but in this case, they slant upwards to the right. The isobars, or the height lines, are slightly curved, still pretty much horizontal, but they've got a slight curve to them. Mixing ratio and a slant upwards to the right, not as much as the isotherms or the temperature lines. Dry adiabats slant to the left, and same with the moist adiabats, but they've got that characteristic curve. Examples that we've shown in the weather data sources and maybe earlier. Yeah, I guess we haven't actually seen one of those in this presentation yet, but yesterday some of the slides had these SKU-T log Ps on them. And they're used commonly in the United States, so if you go to the University of Wyoming Weather Web, like this example is from, you'll probably see a SKU-T log P. Excuse me. So once again, isotherms rise to the right. Isobars are height pretty much straight across. Mixing ratio rising to the right. The dry adiabats in this case actually curve a little bit, still rising to the left, but they're depicted with a bit of a curve, an upward curve. And the moist adiabats start out curving to the left, but then they bend a little bit more to the right as you get farther up. And, once again, they end up pretty much parallel to the dry adiabats at upper levels of the atmosphere. Just an important point about the last two, the Tephi or T phi diagram and the SKU-T log P, is it does allow a whole range of stability calculations. And you can see an example of a lot of these things just on the right-hand side. There's a whole bunch of different figures there. So a lot of different calculations of stability or instability. A lot of that is related to the potential for shower or thunder shower development, but maybe there can be some other applications as well. Just the advantage of the last two diagrams here is anything that uses what we call a lifted index. There's the LI, which is just lifted index. Here it's just signified as lift or lift V using a virtual temperature below that, or a little bit farther down the Cape or the Cape V. They're all lifted indexes, and the simpler thermodynamic diagrams won't allow that type of calculation, but these more complex ones do so, much more versatile type of thermodynamic diagram. We won't really be going into the details of using these here, but have a very basic introduction, and we'll use the very simple STUV diagram for these exercises. I'm just going to skip through these lines again and get on to the STUV diagram, which originated in Europe again. We can't depict the lifted stability parameters such as Cape, but we can plot, simple things like temperature with height and determine if there's going to be a unstable or stable layers up above you. So once again, the isotherms are present, vertical lines. The scale is at the bottom here, so these are temperatures in blue. Probably should have pointed that out in the previous diagrams as well. We do have scales at the left and the bottom. Isobars are height, once again, horizontal lines. So in this case, we have a pressure value. So these are in millibars or hectopascals. So we can get the ink to erase. There we go. And mixing ratio. In this particular case, brown dashed line rising slightly to the left. And the dry adiabats fairly steeply to the left in green. And the moist adiabats depicted with the dashed line kind of curving up to the left. All right, so this is what we use in this course here is just kind of a blank Stove diagram plot, and the those files that I pointed out right at the very beginning are exactly this, just in different form. So just down at the bottom here, we've got our temperature scale. In this case, we've got a height scale up the left-hand side, so that's in feet. I don't have a metric equivalent of this diagram, I don't think, but we'll use what we've got here. There's a bit of a key just at the very top here, so we've got the dry adiabats pointed out, solid lines rising to the left, the wet adiabats, kind of the dashed line rising to the left, and dew point lapse rate here is included as well, but we won't really be talking about that in this particular course much. Right, I guess I've got these things all labeled here. So there's the dry adiabat, moist adiabat, and the dew point lapse rate. It's kind of a grayish line in the background there. It can't really tell if it's actually dotted. It might be dotted if you look really closely. So, but it just appears a little bit more gray and slants a bit to the left of those vertical isotherms. Now, if we take a look at a dry adiabat here, if we have temperature plots that stay to the left of that, we're in unstable air, and conversely, on the other side, for temperature plots tend to go to the right a little bit as we go up, so we'd be crossing those vertical lines or maybe staying close to them, then we're in a stable air mass. Might see that term isothermal, which this means the same temperature all the way through. So if we do have plots that follow straight up one of those temperature lines, you're really still on a stable air mass. And the way you can tell that is a potential temperature. So if we take a temperature someplace and follow down the dry adiabat to usually to 1,000 millibars or hectopascals, I'm just going to pretend it's right there. A perfectly dry adiabatic lapse rate indicates neutral stability. So if you're on the right-hand side of that and you follow down a dry adiabat, well, you're going to come out with a higher temperature. So if that potential temperature rises, then you're in stable air. Conversely, if you follow down one in the unstable air mass, you're going to come out with a colder temperature at the surface than what your observation is. So in that case, you're in unstable air. Just another way of telling, if that's a stable or unstable air. I guess, anything that really follows a dry adiabat, I think it's probably pretty rare that you have a plot that would exactly follow that dry adiabat. It might be close. If you're just a tiny bit to the left or right, maybe you can still call that kind of neutrally stable. All right, so we'll just go through some sample plots here. So top one in blue, got -7 degrees Celsius at 10,000 feet. So well, we've got temperature of 0. These are increments of 2, I guess, 2, 4, 6, 7. So, we go up this blue dotted line until we get to 10,000 feet. So that's the first plot in this example. Second one, 10 degrees Celsius at 2,500. Well, we've got the line representing 10 degrees right here, so we just go up that, and I guess, these are increments of 1,000 feet, so we're kind of halfway between that 2,000 and 3,000. So we put our second plot right in the middle there. And on the right-hand side, 31 degrees Celsius at 1,000 feet. So Yeah, 30, these are increments of 2, so halfway between those two, we get that 31 degrees and 1,000 feet, just that first mark up, first line up on the left-hand side, so got a third plot over there. So, fairly simple in this case to plot those things. So we've got the sample helicopter sounding here from Salmon Arm in British Columbia, early August 1998, late in the afternoon. Take a look at the plume. We've got probably pretty vigorous fire activity and good lift right on the side of a mountain slope by the look of it here. So, part of that is lifting up from air below maybe, but driving that plume up a bit higher. And of course, the heat of the fire always has an influence on these as well. All right, so what does our temperature plot look like? Well, close to the surface. Maybe this is the actual surface of the land here, probably sitting at 3,000, or pardon me, these are increments of 1,000, so maybe 1,500 feet or so above the surface. But a temperature pretty close to 30 degrees, so fairly warm day. Next two plots up are a little bit to the left here. But we've got dry adiabats there and there. So if you drew a line through these plots here as well, roughly parallel with those other dry adiabats, maybe at some point there's maybe just a very weak inversion, if that, and might still be fairly neutrally stable there. But if you get up a little bit higher, then maybe there's a little bit more of an angle here, so it looks like we might get into an unstable air mass up in this region here, probably up around 4,000 feet or so. That's maybe what's helping to drive this smoke column over here. I think with the heat of the fire, you're not going to have your helicopter or whatever rising right through the smoke plume, so this might be off to the side a little bit, and maybe there is a weak inversion, but just with that heat from the fire, it might actually bump the temperature up enough to easily break through that. Then, we've got something kind of weird going on just up above that little unstable layer there too. We've got a sudden, probably a bend to the right here, and then another bend to the left. So, maybe once again, there's a bit of a shallow, weak inversion up there, and then another unstable layer up above that. But really, I think that, this upper portion here, for the most part, it's just kind of fairly close to neutrally stable. It pretty much parallels the dry adiabatic lines here. So probably pretty neutral up around there. So, if you do have hot air from the fire or something pushing smoke up into these regions, well, it might get up to a certain height and kind of linger there. And maybe we've got a bit of an inversion at the top of this plot here. So, maybe somewhere up in that section, maybe you'll tend to get that smoke pooling up in that maybe 5,000 to 8,000 foot height. Probably can't really see it in this photograph here, but that's what the thermodynamic diagram is suggesting. I think I've just circled a few of these, so I'll just skip through that. I guess I didn't need to spend too much time drawing on it. I keep forgetting what's animated in here and what is not. So, all right. So another helicopter example here. We've got a bunch of altitudes, both in meters and feet. Temperatures on the right-hand side. Just visually, we've got temperature at, sorry, some reason the highlighter stopped functioning properly. I'm going to try this again. All right, right at the top scale, on top of the scale, we've got 457 meters or 1,500 feet. Temperature of 22 degrees. But look what happens once you get up above that level a little bit. So is that an inversion? Anybody shout out an answer here. Is it an inversion or not an inversion once you get up to around 700 meters or so.
Inversion.
Inversion, definitely. But warmer air as we're rising there. Sorry, I skipped off that slide again. All right, and then once you get up a little bit farther, then we can see the temperature start to cool off again. So, exercise 1 here, we'll just do in class. There's a very similar exercise that you can do in your spare time. I think they're generally fairly simple, so it shouldn't take too long to do. So here we've got all the points animated, so we're going to start out with that 1500. We'll use the scale of feet here. We've got it in feet on the left side of the diagram. So 1500 feet, we're sitting at about 22 degrees. We go up a little bit more, 25, just about 26 degrees, a bit more, just about 30 degrees up there. A little higher, very similar temperature, and then we start to see a little bit of cooling as we get up. So we're sitting up at 5,000 feet at this point here, so the 5,000 foot mark, and sitting at about 25 degrees. Go up a little bit farther, down to 21 degrees, and then at the top of the plot here, 8,500 feet, well, we're down to about 1,600. So, you know, what I've done with the red line here is you can forecast kind of what temperature is needed to break the inversion, and we do have a really sharp inversion down at the lower levels here. So if you had any smoke, inside that layer, well, it's probably going to get trapped fairly readily. I can't remember if this said it was a morning sounding or not. I'm not going to back up. You can maybe look at the PowerPoint, but this is probably pretty typical for morning when you get fairly sharp inversions, and then as you get daytime heating, it tends to heat up the land, and eventually those inversions may break. Sometimes they won't. Sometimes they'll stay in place all day long, but with a good, fairly clear day, warm temperatures, maybe a little bit of atmospheric instability up above, you might get that inversion breaking, and timing is quite critical for that. But here we follow up that dry adiabat, or follow down until we get roughly to the surface. Then, it looks like we need a temperature of about 33 degrees to actually erase or break that inversion. Now, of course, that may be related to the weather itself. Daytime heating, maybe we'll achieve that temperature. It might look pretty typical for a day where you get mid-30 afternoon highs, overnight lows maybe around 20 or so, sometimes a bit warmer depending where you are. So, it looks pretty typical for a fairly good hot weather summer pattern. Now, if you wanted to break that, I guess the rest of the inversion all the way up, probably need a temperature a little closer to 40 degrees, 37, 38 degrees, and to have instability maybe all the way up until the top of that plot. So, yeah, I don't know if you'd achieve that, but definitely the breaking of that inversion around 33 degrees is a distinct possibility. So if we add humidity in here, so we're going back to the skew T log P here, and this is actually a Canadian sounding from Pickle Lake, Ontario, up in northwestern Ontario. The temperature plot is on the right-hand side here, and the dew point is on the left. So, what can we take away from this? Well, first of all, if we have a really big separation between the temperature and the dew point, such as in there, we've got very dry air, so the dew point is low. Temperature might still be fairly warm, but really dry air up there, the dew point really drops off. Then a little bit farther above that, well, we've got moist air up there. The temperature and dew point are a lot closer together, and There are some kind of rules of thumb, with that dew point depression, as we call it, temperature minus dew point, or T minus TD. So, it's within, a certain number of degrees, you can maybe give an estimate of whether there's going to be maybe some minimal cloud or scattered cloud or more continuous cloud. And of course, the closer those get together, the closer to saturation we have the atmosphere at. And right at the very bottom here, we've got that saturation with a question mark, and it's kind of maybe obscuring the very bottom of the plot here, but really looks like the temperature and dew point are awfully close together down there. So fairly good low level moisture, just extending up maybe the first kilometer or so in the atmosphere, and then really dry air above that. And that can have implications again for fire behavior, because if you do get some instability, you can mix that dry air down towards the surface. And even though you start out with fairly good moisture content at the lower levels, it might not hold all the way through. So do have a bit of an inversion right there, around 700 hectopascals or millibars, so a little bit more elevated. It's a ways up in the air. Once again, if that breaks, maybe you can get some convection and thunder shower development, especially with maybe moisture near the surface, and once again up a little bit more in the mid-troposphere, a bit closer to the 500 or 600 hectopascal level. So lots of things you can infer from these diagrams. Something else, is that if you go up through the levels here, you can quite often see areas where there might be slight inversions or slight instability, or maybe with a slight temperature increase, you'll get instability. So, the atmosphere is really like a kind of a thick sandwich with, so many layers of heat and moisture profiles throughout it. So it can be very complex. Something else you'll notice is right at the very top here, we tend to get the temperature plots suddenly veering off to the right. Excuse me. So we get warming temperatures up there. Can anybody suggest why we might see warming temperatures at the very top of the plot? I mean, we're getting up around 15 or 20,000 meters here. Any ideas? I did cover this in the preliminary audio PowerPoint. Anybody listen to it? There's something that lies away up above the surface here in the upper parts of the stratosphere. It's the ozone layer. You start to get additional heating from ozone soaking up solar radiation, so we tend to get heating of the atmosphere once we get up to a certain level there. So quite often these plots, you'll see the top of these profiles bending off to the right. It's pretty consistent. Just along the right here, we also have some wind barbs just showing the wind direction and speed at different levels. And once again, I've mentioned all the stability indexes at the far right-hand side. Once again, this is really not pertinent information. It's just really an introduction, and I'm not going to ask any rigorous test questions on this type of material. So we're going to extend the thermodynamic diagrams to other uses. Well, we've talked a lot about stability indexes, and we'll talk about that again a bit in upper area influences next week. Cloud assessments, I mentioned that. Adiabatic heating, so if you have air coming over a mountain range, for example, going to use the adiabatic diagram to determine what temperature you're going to get on the leeward side of the mountain range. Wind profiles I mentioned, and there's probably other applications as well that probably won't go into detail about here. Just a little bit about clouds, stability indicator, cumulus versus stratiform clouds. So cumulus is puffy, it's built up, indicates instability in the atmosphere. Stratiform, kind of a flat layered cloud, better indication of a stable atmosphere. There's a very simple rule of thumb for estimating cloud base height here. So 400 times the difference between the temperature and the dew point, or T minus TD, or dew point depression. So if you get greater than 8,000, then, it's probably got a fairly dry air mass, and less than 4,000, it's probably fairly moist. Different types of cloud levels: low cloud, maybe less than 6,500 feet or 2,000 meters. Mid-level is kind of in that 65, maybe up to 23,000 feet or 2 to 7,000 meters. And, it's really probably splitting hairs, I guess. Some of the cirrus clouds will maybe fall within that mid-level layer, but, I think most of them are classified as high cloud. So, that upper division between the mid-level and high cloud may be a little bit blurry. And just wondering if my mouse battery is getting a little weak. I have to click several times to get something to happen here. Dew point depression can indicate scattered cloud, 6 to 9. T minus TD is in that range. You might have scattered cloud, broken cloud if it's between 3 and 6, and maybe more continuous if that dew point depression is less than 3 degrees. If it's greater than 9 or 10, maybe there's no cloud. All right, so just kind of a review of what we've done here. We've brought out the definitions and conditions of stability using the air parcel concept, introduce thermodynamic diagrams. And once again, just the important thing to remember on all those is that they all contain those 5 types of lines. The isotherms or temperature lines, the pressure or height lines, the dry and the moist adiabat, and a mixing ratio line. So mixing ratio is the, if I haven't mentioned it before, is the amount of water vapor per dry air. So, it's usually pretty slight. For sticking with the same units, we usually talk grams per kilogram, grams of water per kilogram of dry air, but it might be kilograms of water per kilogram of dry air. So, I think a normal kind of a summary day will, that mixing ratio, you might have 20 or 30 grams of water per 1 kilogram of dry air. So, if you divide that by 1,000, well, we get a 0.00 something kilograms water per kilogram of dry air. So if I haven't mentioned that before, that's what it really means, that mixing ratio. It is a conserved quantity. So in your air parcel model, if you lift or lower that air parcel, that mixing ratio stays the same there. And that's what can really help us determine, where we get cloud formation and maybe the bottom layer of thunder showers and things like that. So we've done some simple temperature plots, interpret stable and unstable layers. We've looked at a few of those. Some can be fairly dramatic, some can be pretty weak, so we have to look fairly closely sometimes. And I've kind of looked at the dew point and temperature lines and just can estimate the RH relative humidity from the spread as well. So didn't really go into too much detail there. It's just kind of an introductory thing, and maybe not too important to remember great detail about it. Okay, so that brings up the end of this particular section here. So, maybe I'll just go back to the student body, see if there's any questions or discussion.
Richard, I guess just for your information, there isn't anything related to the presentation in the chat, and no one has their hands up.
Yep. All right. Yeah, I've got the crowd back up here again. So, so we're just under an hour on that. Maybe we'll take a few minutes break here. That's kind of an odd minute here. Try about 15 minutes. Let's come back at 5 minutes past the hour. And that's more like 10 minutes. Is that enough? 10-minute break? Yep. All right. If anybody's in Newfoundland, maybe it's 5 minutes past the half hour. See you again shortly. We'll talk about venting.